Welcome back. Unfortunately, I don't have your midterms with me this time. You are welcome to come to my office hours to pick them up on Thursday. Or if you're eager to get them today, you're welcome to come out right after class. I'm going to go to my office at the Jackman Humanities building, which is not far from here. You can come with me and pick up your test. I'm not going to hang around my office. I won't be there till 5 or anything like that. So if you want to come right after class with me to my office, you could pick it up then, or you're welcome to come back at my office hours at any time. So here's the distribution of the test results, the overall test results. The vertical axis is the number of students who achieved that score. Horizontal axis is the score achieved, overall score out of 50. As you can see, you did really, really well, really well. The overall average was 81.9%, which is outrageously high by the standards of this university. Yeah, I would say outrageously high. And a number of people got 100%. So very well done, everyone. Well, on average, everyone. You as an aggregate did very, very well. Yeah. Do you have any questions about this stuff? Any questions about test or whatever? Yeah?
So that is to say, the next exam is going to be off-central?
Yes, yes. So the question is, does this mean the next one's going to be harder? And yes, but not because I'm going to intentionally make it so that you get a bad mark. It's just that as the course progresses, the material gets harder. So this is actually not that unexpected that the average is high. This course tends to start out with a fairly high average, and then it kind of goes down as the course progresses. So don't bank on this being your final mark, but if you did really well on the first test, chances are you'll do really well on the course as a whole, but maybe not necessarily as well. So this average will very likely go down as we go through. The next test will be predicate logic, of course. Predicate logic is harder than sentential logic, and then the exam will be largely multi-place predicate logic, which is harder again than single place predicate logic. So it will continue to get tougher. The averages will probably go down, but you'll be fine. It should be fine. Yeah. I'm sorry, I didn't hear that. Do I tailor the grades? Well, not really. I mean, I certainly don't curve or adjust the grades in any way. I write the tests to produce roughly, the average I'm supposed to be aiming at is 72 or something, so a full 10 points below this. And yeah, I do write the tests to try to produce a reasonable distribution, mostly because of what grades are supposed to be for in the first place. So if half of you got 100% on this test, that means half of you kind of get no information about how well you did in a kind of precise way, so you lose diagnosticity. So the less of a smooth distribution I produce, the less diagnosticity you get. So those of you who got 100%, presumably there are some of you who are much better at logic than others, and you don't get that information. You just maxed it out. So a smooth curve actually has a very useful function in the sense that it gives you helpful feedback on how you're doing. So that's ultimately the purpose of producing a bell curve-ish distribution. But you can see that this is not very bell curve-ish, except in the very high range. Okay. So that was some of the philosophy of grades. Now let's proceed to the philosophy of logic. All right, exercise 7 is posted, due this Saturday, of course. They're all derivations in predicate logic, and I'm sorry to say that we're not going to learn all of the skills for this today. So it might not be the case that you're able to dive in after class today. This will all be ready for Wednesday, but most of these are fairly short, although by the end they get kind of challenging. So they won't hopefully be too onerously long to do, but nonetheless, this will be a good solid week of work to get ready for these. Okay? Okay. So let's begin. Derivations in predicate logic. Okay, so today I'm going to introduce these 3 rules. We've got 2 more rules to learn on Wednesday, and that's basically it for stepping up from sentential logic to predicate logic. So we had, what, 10, 15 rules or so in sentential logic. We're adding about 5 more. So in some sense, this is a fairly incremental step up in terms of the complexity of the derivations that you'll be doing. It's not a wild, humongous leap. We're not learning 5 times more rules or anything like that. These 3. I'm not going to pretend that this is ultra straightforward stuff. It's challenging and there's some ins and outs to learn, but it's not like a humongous leap in complexity. So today we're going to learn universal instantiation, existential generalization, and existential instantiation. Each of these are either an elimination or introduction rule for the quantifiers. So universal instantiation, let's start with this one, where it's the elimination rule for the universal quantifier. That is to say, you've got a sentence with a universal quantifier in it, with a universal quantifier as the main operator, and you apply universal instantiation, and you get out of that something that doesn't have the universal in it. So it eliminates the universal quantifier. Okay. So just to refresh yourselves, recall that this is what the universal quantifier means. It means that we can take the sentence that's universally quantified and plug in names, any name for anything in the entire universe, and the sentence will come out as true. That's the claim being made by a universally quantified sentence, that you could plug in any name for any object and it'll still be a true sentence. Okay, so that means that it's going to be a reasonable move, it's going to be a logically justifiable move to apply it to plug in any name into the quantified variable. So, sorry, that might not have been clear, but here's it in a derivation. So here's the simplest possible derivation that I could think of for a universal instantiation. So you've got this universally quantified sentence for all x if hx then hx then gx, and you've got ha, which is saying the object A has property h. And your goal is to show GA. Okay, so you use universal instantiation on premise 1. And you just strip off the universal, and for every instance of x, you plug in whatever you want to that x. Because the universal says this is going to be true of anything at all, you can plug in anything and it'll be a valid move. So I got HA, I'm trying to get GA. That means it would be convenient for me to have if HA then GA. So I can just universally instantiate that variable to A. So we say UI to A. And from that I get if HA then GA, do my good old-fashioned modus ponens, and I get the thing that I was going for. Yeah? And is it clear why the meaning of the universal quantifier makes this a move that makes sense, that it makes sense that we should be allowed to do this because the universal should be anything you can plug into it. If I have the universal, if I know the universal is true, then I'm allowed to infer that it applies to any given object. You can also do this with a variable. So it doesn't have to be what I just showed you was HA. If I was looking you can universally instantiate to a variable letter as well. Here, I've started with x and I've instantiated to x, and that's fine. There's no problem with that. Again, it should be anything. Universal says this applies to anything. So if it applies to anything, it applies to x, so you can universally instantiate to x. So instead of a name, you can instantiate to a variable. Similarly, you can do it to a different variable. So you don't have to just apply to it's not that you're just allowed to universally instantiate to x, any variable. Any name, any variable. You can universally instantiate to anything you want. Okay, so do some restrictions now. You can UI to any variable, asterisk. There's a little proviso here. or name, because it's true of anything. And there'll be one exception that we'll talk about in just a little bit. I got to introduce a few more things before we can clearly explain the exception. So we'll just come back to that. But restrictions. So this is a restriction that should be fairly familiar by now, because our rules only ever apply to the main operator of the sentence, right? You're not allowed to apply rules to parts of the sentence, just the whole thing. So you can only apply UI to a sentence whose main operator is the universal. And you can only apply it to the main operator. You can't do universal within a universal. So this is no good. This is no good. I've got a universal conjoined in a conjunction with an existential. If I tried to UI to just half of it, that's not allowed, because I've applied a rule to just part of the sentence, not the sentence as a whole. So what you need to do to make it accessible for UI is just simplify it apart, right? You just make it so that the universal is the main operator of the sentence, and then you can apply it. Yeah? So this is just another version of the rule that we've been dealing with all along, that you're only allowed to apply rules to the main operator of the sentence. Okay. Now, one restriction on this is that you can only UI to everything in the sentence. So every instance of the variable must be replaced. You can't pick and choose. You can't do just one. So the following is not allowed. You got for all x if fx and gx, you cannot infer from that if fa then gx. That's not okay. You've only replaced one of the x's there, and you have to replace all of them. So why is that? Yeah, so here's a list of things that are not allowed. Well, one of them is allowed. You can replace all of the x's with a, but you can't replace just one of them, and you can't replace just one of them with a variable name either. Okay, so why is that not allowed? So let's give this an English language version. Okay, but sorry. Let me first go back to the notion of free variables. And yeah, question.
Could you replace the variable a with b, and then the premise was f a f b, but then keep the same rule and change it to f b?
Yeah. So A or B, that's fine. Yeah, that's fine. Yeah. Okay. So let me briefly refresh you on this kind of weird notion of a free variable, because when you universally instantiate to a variable, this is what you get. You get a free variable. You stripped off the quantifier, and you get a free variable. And I've been racking my brains trying to figure out a nice metaphor to explain what a free variable is, because it's kind of like a name. But they're not names for specific known objects. So a free variable is like you're saying, okay, we know somebody burned down the house. Let's call them X. And then you try to gather information about X. So so X is acting like a name. You think that there's a specific object that X is referring to, but it's not like you know the name of the person who burned down the house. Right? You're saying, okay, there's going to be somebody, we know somebody burned down the house. Let's give them an arbitrary name, and then that arbitrary name is a kind of collecting point for information about them as you try to find out who they actually are. So a free variable acts like this. It's like a variable that gets treated temporarily as a name. You say, okay, X is now going to be the name for this thing. We don't know really what it is, but we've got some information about it. So I'm going to come back to free variables. They're going to be important a number of places in the rest of this lecture and on Wednesday. But here's the example. So here's going back to, so remembering the free variables thing. Now, why is it the case that you're not allowed to UI to just one of the instances of a variable? So suppose that this sentence says, if somebody started the fire, then they're guilty. For any person, if that person started the fire, then they're guilty. So if I say, well, if Anne started the fire, then Anne is guilty, that's fine, right? That's a reasonable inference. So if you know the first universal, then you can plug in any name, and so long as you plug it in for every instance, you get something that's also true, or at least truth preserving from the truth of the universal. But what about this inference? So I say to you, well, anyone who started the fire is guilty, and then you say, well, if some person X, that's our free variable, if person X started the fire, then Anne is guilty. That doesn't work, right? Anne will object to this inference, right? Anne was perfectly happy to accept the first one. Yeah, if I started the fire, then I'm guilty. And then you say, well, if anybody started the fire, if some random person started the fire, then Anne is guilty. She's not going to accept that. And she shouldn't. That's an invalid inference, right? From the knowledge that anyone who started the fire is guilty, you don't get to infer that if some random person started the fire, this specific person is guilty. But you do get to infer that if this specific person has started the fire, then that specific person is guilty, right? Is that okay? Okay. And similarly, if some random person Y lit the fire, then some random person X is guilty. That doesn't follow either. You need it to be the same person in both cases. Yeah? Is that clear? Okay. The way this works is dependent on the kind of weird properties of free variables. But hopefully this is an intuitive version. And really all you have to do is just memorize the rule. Anytime you apply UI, it has to be applied to all of the variables with the same letter in that sentence. So, just another example. So it's anything doing UI. You have to universally instantiate to all of the variables under the scope of the quantifier that you're universally instantiating. So I'd have to replace the first x, the jx. I'd also have to replace the kx, because it is also under the scope of the for all x, of the universal. So you have to remember your scope and binding stuff here. This is where that scope and binding stuff, you need to be able to identify which variables are bound to which quantifiers, because you have to instantiate to all of the variables that are bound to the quantifier you're instantiating. So either of those would be fine. Either of those are valid universal instantiations from the top universal, so long as you replace them all. Okay? Yeah? Okay, so you're imagining that there exists a y says there exists an x? All right, let's get this. So, yeah? And h of x, yeah? So now it's a time to remember your, so replace this with, say, y. Yeah? Like that? Yeah, this one is x? Like that? Okay. Okay. So this is a good question. This is to refresh you on your scope and binding rules. So suppose that I'm trying to universally instantiate this first line. Which of those is under the scope of the first universal? This is the one weird exception. So usually it's just whatever's in the brackets, right? With the exception that you can have a smaller quantifier within that takes precedence. So right now, if I'm going to universally instantiate this, it should look like this. hx and kx. So suppose I universally instantiated to A. That's what you should end up with. So if I UI the first line to A, because the existential takes precedence for what it binds, so the hx and kx are bound to the existential because they're the smallest ones whose scope it falls under, not the universal. Right? So this is just the scope and binding stuff that we did before. Does that make sense? Okay, good. Okay. So, just to review what we just did, you UI to every instance of the variable that's within the scope of the quantifier you're UIing, and you only UI to the scope of the main operator of the sentence. And also one other thing that we haven't talked about, and we'll talk about in a minute. Okay? Okay. Okay, so that was universal instantiation. Let's do existential generalization now. So EI is the introduction rule for existentials. So you have something that is not quantified, and you want to build an existential. You want to get an existential. The rule you're going to use is existential generalization. So just intuitively, here's how this rule works. You've got a sentence that asserts that an object has a property. Now, you can generalize from that to the fact that there exists at least one object with that property. So, Dave has long hair and a good job. So suppose D stands for Dave, L is long hair, and G is good job. So we'll symbolize that as LD and GD. Now, do you find it reasonable to infer, suppose that it's true that Dave has long hair and a good job, does that make it true that there exists at least one object in the universe that has long hair and a good job? Yes, it should. Right? Perfectly justified. You seem to have actually, and any of these inferences, you should have the feeling that you said less in the second thing than the first thing. That's the basic principle of derivations, that at no point do you say more than you started with. Right? So saying Dave has a good long hair and a good job says more than there exists at least one object that has long hair and a good job. So you can only ever say the same amount or less when you make one of these inferences. That's exactly how a derivation works. You're never helping yourself to more information than you started with. Okay. Now, unlike universal instantiation, you don't need to existentially generalize to every instance of the thing. So we're also justified in saying there exists at least one thing that has a good job, and also Dave has long hair. That's saying even less than the first existential that we talked about. Okay, we're saying, look, there's at least one object that has a good job, and also Dave has long hair. That's perfectly well justified. That's saying less than the first thing, which is Dave has both of these properties, right? So when we're existentially generalizing, it's okay to just generalize over one or two. You can pick and choose how many of the instances of the object you want to generalize to. You can also say, obviously, there exists something that has a good job and Dave has long hair. You can do the opposite as well, of course. Sorry. So you could say there exists at least one thing that has a good job and Dave has long hair. Yeah. Sorry. Okay. At least one restriction on this. The introduced existential has to have scope over the whole formula. So all I'm saying here is that you don't get to generate free variables with this rule. So if I have HA and JA, I can perfectly well, sorry, HA or JA, I can existentially generalize to there exists something such that HX or JX, but the scope of that first quantifier, the scope of the quantifier only ranges over H. It's got to range over the whole thing that you're generalizing. So that's what was up there is wrong because we haven't done the whole thing. So you're not, basically the thing to keep in mind, you're not allowed to generate free variables with existential generalization. You're introducing an existential, it's got to have scope over everything that you're generalizing over. Anytime you replace the names with a variable, that existential has to have, its scope has to contain the variable you introduced. That should be okay, yeah? Okay. Okay. And here's the thing that I've been hinting at. Here's one more restriction. Pardon me. Excuse me. All right. Here's the no capturing rule. It's not a rule that comes up a lot, but nonetheless, it's an important one. Here's the textbook version of this. When using rule UI or rule EG, a new variable must not be introduced if some of its new occurrences are bound by a quantifier in the original formula. Okay. This textbook is great. It's free. Sometimes the writing is maybe not as clear as you would hope. This is nonetheless the rigorous definition of the no capturing rule. Let me show you it, and hopefully it will be clearer than that sentence is. So, these are both introduction rules. UI and EG, you're potentially introducing variables. Sorry, UI is not an introduction, it's elimination, but it can nonetheless introduce variables. So these variables must not already fall under the scope of a quantifier inside the sentence. What does that look like? Okay, let's start from this sentence. All jackals are hungry and there exist carrots. That's a true sentence, right? No, it's not true. It's not true that all jackals are hungry, but suppose they were. A reasonable enough sentence, not a bizarre sentence, hopefully. Okay, now I'm going to universally instantiate that first x, that for all x, I'm going to universally instantiate that to y. And that's going to be disastrous for us. So that's capturing. So if I universally instantiate that x to y, here's what happens. So if jy, then there exists something such that cy and hy. So we started from all jackals are hungry and there exist carrots. And we inferred from that that if something is a jackal, then it is hungry and a carrot. Does that strike you as a valid inference? Does that strike you as something contained within the first sentence? It should not. It should not. What's happened here? What's gone wrong? So what's gone wrong is the following. So we've got, it's a weirdly written sentence. The first sentence has been symbolized in a weird order. We've got this hx. So this hx is bound to this for all x. So when we universally instantiate, we have to replace all the x's with whatever we're instantiating to. But it's like we've reached inside the existential and said, hey, existential, now you apply to this thing. And furthermore, that existential, we've said it applies to this thing, and it's the same thing that cy is. Right? So we're saying the jackal is a carrot. That's wrong, right? Okay. So basically, you've by universally instantiating to something that's already bound to the scope of a quantifier inside the sentence, you're giving yourself more information than you started with, which is exactly the thing that you don't want to do in a derivation. You never generate new information by doing a derivation. You just pull out the consequences of what you already know. So what that first sentence doesn't tell us, what this universal here does not tell us, is that the object corresponding to x is the same object that corresponds to y. That sentence doesn't give us that information. But by UIing to y, we have helped ourselves to that information. We've helped ourselves to the idea that the jackal is a carrot, which is not contained in the original sentence. So it's not always going to be the case that universally instantiating to something that is already a variable inside your sentence is going to cause this kind of confusion, but we rule it out. We have a rule against it, the no capturing rule, in order to make sure we never do something like this. Okay, let me go back to the, so now that you've seen it, let's do the rule again, see if it makes more sense this time. When using rule UI or rule EG, a new variable must not be introduced if some of its new occurrences are bound by a quantifier in the original formula. So if you've got a quantifier, you've got a quantifier within a quantifier. That inside one has a variable associated with it. You're not allowed to UI or EG to that, because that's helping yourself to more information than you started with. It's helping yourself to the idea that those two things are the same thing when you don't know that yet. How's that? Yeah. How should you do it? You should, so in a case like this, you're allowed to UI to literally anything except for Y. Anything except for Y. So the no capturing rule tells us you can't UI that first sentence to Y, but anything else is okay. Yeah? So if you don't want to universally instantiate to a name, so that JY is a free variable, and it's, so that's saying, like, suppose there's some Y that the thing J applies to. It's free variables, in this case, you're supposed to have no prior beliefs about, basically. So you need something fresh to UI to. So literally anything except Y would be fine here. Like, it's not going to come up much, this one, I promise. But nonetheless, important to understand. It's important to understand because, like, this is how derivations work. That is, we're pulling out less informative sentences than the ones we started with, and this is pulling out a more informative sentence, which is against our rules. Okay? Okay. Okay, so to review existential generalization, you don't have to EG to every instance of the variable. So this is different than UI. UI, you have to UI to every instance of the variable. EG, you don't have to do that. But the introduced existential must have scope over the whole sentence, and you're not allowed, the no capturing rule is also a restriction on EG, just like it is also on UI. Okay? Okay. Okay, one more rule to deal with. We'll do this, and then we'll do examples. So, existential instantiation is a rule for the elimination of existential. So you have an existential, and you want to eliminate it. You're allowed to suppose that there is something that instantiates the existential. So if I say, there exists a dog who can read. Now, what we're doing, what you're allowed to infer from that is to say, suppose there's some object, I, and that object has the properties of being a dog and being able to read. This is like our mystery person. Say somebody burned down the house. Let's call them person X, right? So you're saying, okay, there's at least one thing that, you know, this sentence says there's at least one thing that's a dog and can read. Let's call that thing I. And then you can make further inferences about it. Okay. So this is just the form of the inference. There exists an X such that Lx and Dx. Therefore, Li and Di. Right, we just picked a variable and said, all right, let's call the thing that satisfies this I. Now, the really important thing here is that it's got to be an arbitrary thing. Must be an arbitrary thing. And we're going to have strict rules about what counts as arbitrary. So here's what goes terribly wrong if you, oh yeah, and you must EI to all of the instances within the scope. So when you're EIing, just like with UI, you got to do them all. Okay. And you can't EI to a name. So names versus variables. From the sentence, there exists something such that it's a dog and it can read. You're not allowed to infer that, like, my dog can read, or your dog can read, or some dog that you know. You can't. So there exists something such that as a person has been on the moon, you're not allowed to infer from that that it's me, right? You can't go, well, there's at least one person who's walked on the moon, therefore I've walked on the moon. That's not a valid inference, right? Yeah.
Could you apply EI if it wasn't a conjunction, if it was like a conditional or a disjunction?
No, no. Well, oh, sorry. To a name or just at all?
Like if that formula was LX, then DX.
Oh yeah. So what the structure of the formula? It doesn't matter. You're always anything in the existential. You're allowed to existentially instantiate, just not to names. It's just the name. Right now I'm just doing the names versus variables. But if it was if LX then DX, you could totally existentially instantiate to that, no problem. Yeah. Okay. Does the names thing make sense? Right? Just because there's at least one thing doesn't mean that you know which thing it is. So that's why we need a variable and why it needs to be arbitrary. Yeah. So it's just a variable, so from I to Z. And furthermore, so I have a more to say, so I have a couple slides on exactly your question. So let's do that now. It has to be an arbitrary variable, which arbitrariness is going to be defined very strongly here. So we need to talk about what makes a variable arbitrary. A variable is arbitrary when it does not appear free in an available line or a premise cited in an available line. That's a very strong restriction. Basically, you're going to EI to something that's fresh. The easy way of doing this is just to EI to something that appears nowhere at all in the proof. If you see it on the page, don't EI to it. EI to something totally new. Okay, so why do we have that restriction? Why does it have to be something arbitrary in this quite strong sense? So here's what goes wrong if you don't pick an arbitrary variable. So the first sentence, let's say it says, there is something that is a boy and a dog. Let's suppose that dogs can be boys. The second sentence says, there exists something that is good and a ferret. Reasonable enough, yeah? Okay, so I'm going to existentially instantiate the first thing to I, BI, and DI. So let's, whatever this boy-dog entity is, let's call it I. Okay, fine. But what if I then existentially instantiate to I again? Now we've got the idea that there is something that is a dog and a ferret, and a good and a boy. So by not choosing an arbitrary variable, we can get ourselves in trouble. We can help ourselves to more information than we started with. So again, go back to the somebody started the fire example. So if somebody started the fire, then they're guilty. And suppose that we've got, so we say, okay, we're going to existentially instantiate. So we're going to universally instantiate to I. Right? So there exists at least one person whose name is Anne. And now we're going to existentially instantiate. There exists at least one person whose name is Anne and started the fire. Right? You're just getting more information than you started with. So it's about the free variable stuff, right? It's about the way free variables act They act like pseudonames. They act like semi-names. They are stand-ins for a name. And when we EI to something, we're doing this thing. We're saying, look, there's at least one thing that's both a dog and a boy. Let's call it I. But what you don't have the information for is saying, and there's at least one thing that's a ferret and good, and that it's the same object. So when you existentially instantiate both to I, what you're helping yourself to is the idea that they're the same object. And that's not justified from the premises. Okay, so again, if the rationale is not clear, feel free to just memorize the rule that anytime you use the EI rule, you do it to something fresh. Do it to something you haven't seen before in the proof. Do it to something that hasn't been used before, free. So appearing free is like, and that's why you can only EI to something that hasn't appeared free in an available line. Because appearing free is acting as a kind of pseudonym. And you don't want to learn more about your pseudonym than you're allowed to. Okay, so you must EI to all instances of the variable under the scope of the quantifier. And you can EI to any arbitrary variable. Got to be something fresh. You cannot EI to a name or a variable that already appears in the proof, appears free in the proof, I should say. Okay. So that's kind of a lot to have absorbed without using it. So mostly we'll take a break right after. I got one more thing to tell you, and then we'll take a break and we'll do some examples. So on the relationship between EI and UI, exactly because of this arbitrariness stuff that I was just telling you. So EI is in some sense a really easy rule to use because you don't get any choice. You have to EI to something you've never seen before. You have to, right? It has to be arbitrary. It has to be something you have no information about. So you just pick a thing, I, J, K, doesn't matter. Pick a thing. There's no strategy involved in deciding what to EI to. There can be strategy involved in deciding what to UI to. You have to figure out what the best thing to UI. You can UI to anything. You've got loads of choice here. So now you have to do some strategy. You have to be thinking about what's the right thing to UI to. I mean, it's low stakes in the sense that you can UI from the same universal, you can UI over and over again. So it's not like you get trapped or anything, but you do have to make choices about what you're going to UI to. Now, once you've UI'd to something, it's appeared free in the proof, which means that after you've done the UI, you're not allowed to EI to that thing. Right? So if you do UI first, you're cutting off, you can't EI to that thing. So the thing to do is to EI to a variable first, and then UI to match that. So I'm going to EI to I, I'll then UI to I to match it. So the order matters a lot. Basically, the rule is EI first. Basically, whenever you see an existential, whenever you have an existential in one of these proofs, you're going to right away existentially instantiate it. Because that's how you prevent it from being no longer arbitrary. You preserve the arbitrariness by EIing right away. So that's the rule. EI first, UI to match. Okay. Again, this is all pretty abstract until you see it in motion, so I propose that we now take a break, come back in 10 minutes, and we'll start doing some examples of this stuff. So come back at 4:05. So just going to do a couple of examples of this, well, 3 examples of this, to hopefully illustrate some of what we just talked about. Okay. So here's our very first derivation in predicate logic. You'll look back on these days with fond nostalgia, back when life was simple. You only had one-place predicates. Okay. Okay. And just just a reminder, all of the stuff that you learned in sentential logic is all still valid. All of that still applies here in predicate logic. So if you could make a move in sentential logic, you can make it in predicate logic. We've just got a couple new rules to introduce. Okay, and the structure, the basic structure of the proof is exactly the same. Let's show there exists an x such that if gx, then fx. Okay. Now, you could assume ID this. I'll just leave it out for simplicity. The assume ID doesn't do much for us at the moment. Now, we've got one premise. It's an existential. And if you recall, the rule that I gave you just before break was if you have an existential, the thing to do is instantiate it. You instantiate it pretty much right away to preserve its arbitrariness. So we're going to instantiate there exists an x such that fx. We're going to use EI on that. And what are we going to EI it to? And the answer is just something we've never seen before. Something that's not in the proof yet. My go-to is I. So I'm going to say premise 1, EI, and that's going to give us FI. Yeah? Okay, so that's just kind of an automatic move. If you've got an existential, you instantiate it. Okay, now I'm out of moves. Now it's time to start thinking about where I'm trying to go and how I'm going to get there. So what am I trying to get here? The basic thing I'm trying to get is an existential. How do you get an existential? You use our existential introduction rule, which is existential generalization. Okay, so to do an existential generalization, to get this thing, we need something that matches the insides. So we're going to try to build the insides of the existential. So it's going to be if G square, then F square. We just need something to plug into those squares, and then we take that and existentially generalize it. Or if you're feeling mathy, you could say G phi, then F phi. Okay, so we just need something that matches the basic structure of the insides of this, and then we're going to existentially generalize to it. Now, the thing that we've got here is Fi. So probably phi is going to equal I, right? There's nothing else. We have no other options here. Okay. So we do this basic rules if you want. You could just say show if GI, then FI. And give ourselves GI, assume for conditional. And then to repeat. CD. Yeah? Or if you're feeling derived rulesy, we could do the following. Suppose you didn't want to do that. I'm sorry, is that annoying when should I not erase bits because you're writing it down? Yeah, okay, okay. Sorry, I just realized that people are like frantically making notes. Okay, so, okay. All right, show this thing. We got GI, we're going to assume that for CD. I'll just do it in a kind of slow plotting way. Show FI, to repeat, direct derivation. There's that. And then 5, conditional derivation, did that. Okay. Okay, so we showed on the basis of having FI, we showed if GI then FI. That should all be fairly, that's stuff we did back in sentential logic, right? Okay, now we've got if GI then FI, which is a structural match for the existential that we're trying to build, right? It's the right shape of thing to turn into the existential. So we say line 3, e.g. And then we get there exists an x such that if gx, then fx, which is, of course, the thing that we're trying to show. Okay. Very first derivation in predicate logic. So you can see all the old sentential stuff is still in play. Hope you didn't forget it over reading week. The things to do, so in this case, the thing to note is that just to remember how you get things like an existential. How do you get an existential? You get an existential by existentially generalizing something with the same shape, but with different letters, right? So we wanted something. The conclusion of this is just that there's at least one thing that satisfies the following conditional. If gx, then fx. So the way to get that is just to build the thing and then existentially generalize from it. Yeah? Yeah.
If you said there exists an I such that GI then FI, would that also count?
There exists an I such that GI and FI. Oh, so on line 8?
Yeah, because you've used I throughout.
Yeah, no, you don't want to do that. You don't want to do that. So if these are I's, then what you haven't done is derive the conclusion. It's got to be the exact conclusion. So just there exists, the variables have to match as well. Yeah, so that's why you don't want to do that. Yeah. Yeah. Yes, yes. So of these 3 rules that we've introduced today, these are all considered, in some sense, basic rules. These are basic rules. So they're basic rules because you can't derive them from any of our other rules, which means that they're not derived rules. So the derived rules all have the quality that you could do without them if you really didn't care how much paper you used up. Whereas these are rules, like if I didn't have existential generalization, there's just no way I could have solved this. There's no way of getting an existential without doing existential generalization. So these are, the 3 that we've done today are all derived rules. Or sorry, the exact opposite of what I just said. They are all basic rules. Yeah, yeah, yeah.
Could we have done this proof maybe like 30 minutes and using the negation of conditional?
Uh,
Making the existential the first one and running the contradiction.
right, right. So what you're asking, I'm gonna erase it anyway because you all wrote it down already. So what you're asking is if we could start this with assume ID. So it's not the case that there exists an x such that gx then fx. So, and then assume ID. So where we're going to go to next time is learn a rule that would make this useful. But currently I've not yet introduced a rule. So you're not allowed to say negation of conditional here.
You can't say for all x that GS and
Not yet. So that would be what we'll do next time is get the following. Then fx, but that's not negation of conditional, that's quantifier negation. That's qn. So once we have qn in our package of skills, the assume ID will make a lot of sense there, and you'll be able to use it, I think just exactly in the way that you're imagining, but it's qn rather than nc, because this sentence, line 2, is not a conditional. It's not a conditional, it's a negated existential. So the main operator of that sentence is the negation, and if you stripped off the negation, then it's an existential. So you can only do rules that apply to negations on the sentence that is the main operator is a negation. So negation of conditional is not a conditional. There's at least 2 layers under which the conditional is buried here. So you're not allowed to like dig in and work with the parts of it. But once we got here, yeah, we'd be in pretty good shape actually. So we could say we'd still have to do premise 1 EI. So we get FI, and then we could say line 3, we would UI that and get, it's not the case that, oh, sorry, if GX, then FX, and then you could negation of conditional that, generate a contradiction. So your instinct is right that that's going to be a useful way of proceeding, but not until we get quantifier negation on the table. Yeah. Okay. Any other questions? We want to do another one? Oh, actually, while your minds are still as fresh as they can be after an hour and a bit of lecture, I want to show you the same thing on Logic 2010, because existential generalization trips a lot of people up on how to actually do this. So I want to show you the controls for Logic 2010 right now before we get too lost in other things. Okay, so just exact same question that we just did, yeah? Okay, so show conclusion, premise 1 EI. Okay, so please specify the instantial variable, i.e. the variable to which you wish to instantiate the quantifier phrase EX. I choose I. That's going to be my variable. Okay, so EI is fairly straightforward. EG is a kind of weird, tricky one. So let's see, we got, here's how I was going to solve it. Not GI. What? Sorry. Not GI. Somebody tutting me? Is that what's going on? Okay. Okay. So now we got if GI then FI, and now we're going to existentially generalize it. Here's the bit that trips a ton of people up. Okay, so please specify the free occurrences of the term on which you wish to generalize by highlighting each such occurrence by pressing Alt-1. Okay, so here's what you got to do. We're going to go and select, so you see that's highlighted now, select the I, just the variable, not the predicate, and I'm going to hold Alt and press 1. And then that curly bracket 1 shows up. That means you did it right. You have to do that to every instance that you want to existentially generalize over. So I can use my mouse to select if you want. Hold Alt, press 1, and the little curly 1s show up. Okay? And then it'll ask me what variable I want to stick in there, and I want to stick in X. Okay. Here's what happens if you don't do that. So for EG, if I just go ahead and press OK, and then stick X in here, it gives me there exists an X such that if GI, then FI. And that's not right. That's not what you want. Yeah? I cannot tell you how many people were on Quarkus last semester being like, I can't get EG to work. And it's because you've got this sort of 3-step finicky thing to do to get it to work. Yeah? So that's it. If that happens to you, that's no good. So for EG, oh. Okay, again, highlight Alt-1. If you do just one and not the other, then it will existentially generalize to just one and not the other. So you got to do all of the instances that you want to existentially generalize. Built into this is a kind of helpful reminder of what you're allowed to do or not allowed to do with the various rules here. So it asks you which instances you want to existentially generalize because you have a choice about that. You can choose to existentially generalize some but not others, which is why it has to ask you. So this is a nice, every time you use this rule on Logic 2010, you're going to get a little reminder that you have choice about EG. you don't have choice about EI. So recall when I said premise 1 EI, even if this had been a bunch of different things, it only asks you what variable you want to do, and it does it to all of them automatically, because you do not have choice about this one. You must do it to all of them. Same with UI. It'll ask you what variable you want to UI to, not which instances. So every time you use these rules on Logic 2010, there's your little reminder. Am I allowed to pick and choose, or do I have to do them all? Well, it'll ask you about the ones you get to pick and choose on, and it won't ask you about the ones you have to do them all on. So, okay? Okay. So let's do another couple examples by hand. Right. Mildly more complicated. Okay. As always, we're going to show the conclusion. If FA, then there exists an X such that GX and HX. Okay. So just like with good old-fashioned sentential logic, if you have a show line for a conditional, the thing to do almost always, almost inevitably, is to start a conditional derivation. You assume CD, show the consequent. Yeah? So once again, all that sentential stuff is still in play. So we're going to assume FA for conditional derivation. And we're going to show the consequent. And again, once we have cute quantifier negation in play, it would make sense here to attempt to show or to assume ID. But let's just pretend we don't have that yet and proceed trying to just build this existential. So two strategies when you're trying to show an existential, two things that you can do. You can either assume ID and try to generate a contradiction somehow, or you can just try to build the existential. So if I have anything that I can say, if I've got any like G phi and H phi, anything at all, then I can existentially generalize and get that. So that's building the existential. Just get the parts of it and then generalize. The only restriction is that it's got to be the same thing. So having GA and HB is no good to me. I need it to be the same thing in both cases. Okay? Okay, so let's go ahead and try to build this existential. We'll try to get GX and HX. We'll do a survey of our resources as always, try to figure out what we got. Well, we've got a couple of premises this time, that's nice. Of course, we got line 2, and we got premise 1, premise 2. These are beautiful premises to have. I love having universals as a premise because you can just universally instantiate them till you're blue in the face. You can universally instantiate them as many times to as many different things as you want. Lovely to have universals. In this case, what's the only thing? There's only one thing that it really makes sense to universally instantiate these to. A. Yeah? It's the only thing that really makes sense here. I mean, there's nothing, so I can go ahead and say, you know, if fx then gx, that's fine. Premise 1 UI. Doesn't hurt me exactly, but it doesn't really help much either because I don't have the antecedent or the negation of the consequent. There's really very little I can do with that, right? But if I have fa then ga, now I got something worthwhile. Premise 1 UI. And again, nothing wrong with UIing the same thing to do two different things. That's perfectly fine. Sometimes it'll be necessary to UI to two different things. Okay. And I'll just do the same thing with premise 2. If GA, then HA. Premise 2 UI. And now I've got some nice sentential logic moves I can make. I've got FA, so I can say to repeat 5 modus ponens to give me GA. Now I can say 6, 7 modus ponens to give me HA. Cool. Okay. So that was me just kind of like pulling, what have I got? What can I do with it? Pulling stuff out, making moves that seem clear. Now it's a good time to take a step back, try to remember, where am I? What's going on? What am I trying to do again? Oh yeah, my latest show line. Just find your latest show line, line 3, trying to show an existential. And what were we looking for? Well, we were looking for something that fits this pattern so that we can existentially generalize and get line 3. So can we build this sentence somehow? Yes, we can. Yes, we can. Because we've got GA and HA. We're just going to adjoin them together. ADJ giving us GA and HA. So now we're pretty much there. We're pretty much there. We can see light at the end of the tunnel. 9 EG, we're going to existentially generalize that to there exists an X such that GX and HX. And then it's just a matter of closing off our subderivations. So we did this. So on line 10, we did a direct derivation. Array. And then on line 3, we did a conditional derivation. Hooray. Any questions? No questions. Impossible. Okay. Okay, we'll do if there's nothing, we'll do the last example. I'm only going to do one more example. Unfortunately, there's fairly few derivations in predicate logic that don't involve the stuff we're going to do on Wednesday. So there's not that many examples that you can like, any examples, further examples would just kind of be repetitions of all this stuff. So looks like we're getting out early today. Unless we get into a terrible, fraught debate. Okay. A theorem this time. A theorem this time. We got no premises. Okay. I'm going to show this whole big funky thing. X, then this X fx, then there exists an X such that Gx. Okay. So, what's the main operator of this sentence? What is this thing? All together now? Conditional. Wow, that worked. Neat. Cool. Okay. Okay. Yes. Yes. So it's a conditional. Very good. This is the main operator here. So what do we do when we have a show line for a conditional? Of course, we start a conditional derivation. So we're allowed to assume this universal. I'm going to assume that for conditional derivation and try to show there exists an X such that fx. Try to make those X's. There exists an X such that Gx. Once again, we got a show line that's a conditional. So once again, we start a conditional derivation. And we're going to try to show there exists an X such that Gx. Okay. Okay. So we've got, let's do our we've set up our show lines. We've done all of the obvious automatic moves. Now it's time to survey our resources, see what we got, see what we can do with it. So we've got line 2 is available line. Line 4 is an available line. And that's it. All we got is 2 and 4. Okay. So we're going to do something with line 2 and or line 4. Now, recall before what I told you just before the break. I gave you a rule, a very important rule. It's a derivation strategy rule. How do we get through this? What do we do first? We existentially instantiate. EI first, then UI to match it. Because here's the disastrous thing. Here's what you don't want to do. So don't write this bit down. I'm going to erase it in a second. Okay, so here's what you don't want to do. You don't want to UI premise 2, line 2, and then try to EI to match that. Line 4, EI. Because this is not good. That's no good. What you've done is EI'd to something that's not fresh. You need a shiny, new, fresh variable. You EI'd to something that appears already in your proof, and that is not allowed. Right? So I've trapped myself. Don't do that. The thing to do is to existentially instantiate first. So we're going to say line 4, EI. I'll EI to K. Why not? Just whatever variable you've never seen before. You don't have to think about what to EI to. You just EI to something or other, whatever. Okay? As long as it's a variable. Yeah? Yes, thank you. Thank you. 4 repeats EI. Okay. Okay, now we can universally instantiate to match this thing. So we've still got this. We can say line 2, repeat UI. So FK, then GK. And then our good old sentential logic moves, GK. Yeah? Okay. And now we've achieved our goal of generating at least one object that has the property G. We get at least one thing that's G. We know that K has the property G. And that means we can existentially generalize. So 8, e.g., there exists an X such that Gx. And there's our direct derivation. Yeah? And then it's just a matter of closing off these conditional derivations. 5 CD. Three CD. Ta-da. Okay, so things to remember here. Always remember, okay, so derivation strategy here. You've got automatic moves, totally automatic moves that you just make every time you start. So if you've got a show line that's a conditional, you start a conditional derivation. If you've got something that's not a conditional, you typically start an indirect derivation. We'll start doing that when we introduce quantifier negation here. If you've got but new automatic moves that we've introduced today, so you're used to the idea that there are some things that you just do right off the bat. Today we've introduced a new automatic move. If you have an existential, you instantiate it right off the bat. Do it quickly so you don't get drawn into things that would make its variable no longer arbitrary. And then you just proceed. Proceed to survey your resources, try to figure out where you're going. In this case, where we're going is largely trying to build existentials. That is, you're trying to find something that matches exactly the structure of the existential that you're going to then generalize to. Questions? Okay, let's call it a day then. Thanks, everyone.